Hello, this is Kuntal Chakraborty, Assistant Professor of Electrical Engineering Department, Greater Kolkata College of Engineering and Management, JIS Group. I'm just going to give a lecture on 8051 microcontroller programming. I already discussed different types of programming in my previous lectures, like loop programming, programming using branch instructions, programming for delay, different port programming. Now in this lecture I'm just going to discuss some bit manipulated port instructions and some arithmetic program, and first we will try to write some program by using bit manipulation instructions. So first program is toggling the bit of P2.3 continuously. So a particular bit that can be set as well as reset, as we already discussed in the instruction set, that a bit can be set by using an instruction that is set B, as well as we can clear a particular bit, that is CLR. Now here the port 2's point, 3 numbers point per pin that can be set as well as clear. Now we have to toggle all the bits of P2.3, means we have to set as well as clear a particular bit continuously. Now in this instructions we actually set B P2.3, it means at that time P2.3 that will be set as 1. Now we will call a delay, means a subroutine that will be called. A delay program is written into a particular address. Then we will clear P2.3, means if we write clear P2.3, then P2.3 that will be equal to 0. So now again we will call a delay, and that is written into a particular address. Then this subroutine is called. After that it will return into the next instructions, that is jump again. It means basically it will jump to the program sequence that will be transferred here, and again it will perform set B P2.3. Means a particular bit is set as 1, and then it will clear, and it will continuously doing this work by using this program. So that's why the toggling is happening in case of P2.3 pin. Next, set B P0.1, we are clearing a particular bit P0.1 like previous one P2.3. Any port that pin of any particular pin that can be set as well as resets. So this is another program of toggling. P0.1 bit here is actually continuously toggling. So here set B P0.1 means it will be set as 1, and we will call a delay, then we will clear the P0.1, then we will again call delay and sjump again, then it will continuously doing the work. Next bit manipulation instruction is ORG, that is the starting address, start MOV P3, A, means content of the accumulator that will be sent to the port 3. Now here JNB P1.0, here basically we will try to find out the 0 pin of port 1, whether it is set as 1 or not, means this bit is 1 or not. If it is not, then basically the loop is continuously rotated through within the line, and if it is 1, then it will set BP 2.5, means the pin number 5 of port 2 that will be set as 1. If a buzzer is connected with this pin, so the buzzer that will be on, and again we will call a delay, and it will continuously the buzzer that will be on and for a particular time. Then we will clear P2.5 and sjump start. So now this is the way a particular bit can be set as well as reset. So this is a bit manipulation program. So now in this program is basically, by using this program we can check a particular bit, and if it is 1 or not. If it is 1, then we can perform another task, that is here is basically we have set a particular bit of port 2, means 2.5 bit. So a signal or a buzzer is connected with this pin. It may be on for a particular time, then we will clear the bit. So it is actually continuously monitoring the bit. So this is a bit manipulation program. Next is an arithmetic program. First arithmetic program we will start, but first we have to get an idea about the signed number. In signed number, basically the D7 bit, that is the MSB of D7, if it is 0, then the number is basically positive number. If it is 1, then the number is basically the negative 1. So the positive number, that is range, is basically 0 to plus 127, but in case of negative number, the D7 that will set as 1. And basically the magnitude is represented in the 2's complement here, and basically the negative number, the conversion of the negative number is basically done. We have to write the magnitude of the number in 8-bit binary number, and then we have to invert each bit, means 1's complement done, and we have to add 1 so that the 2's complement may done. So that is the way by which the negative number, a number that can be converted into a negative number. So that is the signed number. So in this diagram we are seeing that 0 to 127 is a range of positive number, and every time we are getting the MSB as 0. And for the negative one, from 128 to -1, that is the negative number, and here every time the MSB is set as 1, and this is a binary representation and this is a decimal representation. So decimal representation for -128 to -1 is basically 128 to 255, but in case of positive numbers, that is from 0 to 127 for 0 to 11067 of signed numbers. And these are the binary representations. Now we will try to write some program, arithmetic program. So first we will try to write a program of 8-bit additions, 2 8-bit numbers that will be added by this program. So here the origin address is here, that is the starting address, MOV A, 44H. It means the content of 44H, that is the RAM location that will be stored into the accumulator. Add A45H, so it means the content of 44 that is stored into already into accumulator, and the content of 45H is there. So the addition done between the content of A and content of 45H, and the result that will be stored into the accumulator. So here the carry may be generated, so we have to keep in mind all this about this carry. So MOV 46HA, it means the result that is stored in A that will be stored into 46H, and now we have to consider the carry MOV A, 00. Now we initiate the accumulator here, so I already sent the result into the 46 without the carry. So now we have to write the carry into another location, next locations of the RAM. So that's why 00 is stored into the accumulator. We actually initiate the accumulator by 0, and now we will try to find out whether the carry is generated or not. So that's why we will use @CA, 008, means the content of the accumulator is 0, 0, 0 we are providing, and if there is any carry, then 1, 0, 0, 0, 0 that will be added, and we will get the result accumulator as 1. So if it is not, then accumulator result will be 0. So the content of the accumulator that will be sent to the 47H, that is the RAM location. So the carry result that will be stored into the 47H. So that is the way the 8-bit data, 2 8-bit data that can be added by using 8051 microcontroller. Next is a 16-bit addition. So here this is the origin address, and the content of 51H, that is the RAM location, that will be stored into the accumulator, and the content of 55H that will be stored into the accumulator, added with the content of A, and the result that will be stored into the accumulator. And this is basically the lower byte of that is stored into 51 and 55H. Next, the two upper byte, that is 52 and 56H, are stored into these locations. Two upper byte of these two data, that is 52 and 56H. Basically, our data is stored, fast data is stored into 51 and 52H, where the lower byte of data is stored into 51H, and the higher byte of data that is stored into 52H. And for the second data, that is the lower byte that is stored into 55H and higher byte that is stored into 56H. So we are practically adding the lower byte, two lower byte of data. So after addition, the result that will be stored into A. Now we will send the data, the result that will be into 40H, into the RAM locations 40H. Now, if carry in this addition, carry may be generated, so that's why otherwise no, the carry may not generated. So we have to consider the carry. So now next is the MOV A, 52H, that is the upper byte of the fast data that is stored into the accumulator, and we will add the data with the content of 56H, that is the upper byte of the second data, and we will add the data with the content of A, with considering the carry. That's why we have to use add C here. So the carry is added with these two data, and the result that will be stored into the accumulator, and the result that will be stored into the next address, that is 41H. So at that addition, again the carry may be generated. So that's why we have to check the carry whether it is generated or not. Then we have to copy into a next address. So here 00 is added, stored into the accumulator, means we initiate the accumulator as 0. Then we will use @C A, has 0, means here the content of A is 0 and we are adding 0. And if the carry is generated, then then the carry will be 1. So after addition, so the accumulator will be 1. If carry is not generated, so the carry will be 0. So at that time, the content of the accumulator, after addition, the content of the accumulator will be 0. So whatever it may be the result that is stored into the accumulator, and that will be sent to the 42H, that is the next memory, RAM memory locations. So that is the way, that is a 16-bit addition that can be done. Next is a 16-bit subtraction, and here basically 55H is stored into the accumulator first. Similarly, we are doing the task, and this is a lower byte of data, 55 and 51, that is the lower byte of two data, and 56 and 52 are the higher upper byte of these two data. And here is what is happening here. We actually store the content of the 55H into the accumulator, and we will clear the carry, and then we will subtract the content of 55H to 51H. So we will get the result, and that will be stored into the accumulator. At that time, borrow may be generated, so we have to consider the borrow, and that will be stored into the carry if it is generated. So then the carry that will be set as 1. So now the result that will be stored into the 40H, that is the RAM memory locations. Now we will try to find subtract the upper byte from 56, the content of the 56 to content of the 52. Now 56, the content of the 56 that will be stored into the accumulator, and SUBB A, 52H. So we have to consider the borrow, and that's why we have to consider the carry. So now in this instructions, basically the carry is used, and considering the carry, the data is subtracted from the content of 56 to content of 52, and the result that will be stored into the accumulator. Now the data that will be that can be stored into A to 41H, and similarly we will check whether there is borrow is generated or not. So that's why 00 that will be stored into the accumulator, and next we will use the @C instructions, so that we will check whether borrow is generated or not. If the carry is generated, if carry is set as 1, then we will get the result as 1, otherwise that will be equal to 0, and the result that will be stored into the 42H. So that is the end of subtraction program. Now next is a 8-bit multiplication. So here the ORG00, that is the starting address, and here the content of 70H, that is the RAM location that will be stored into the accumulator, and 71, the content of 71 that will be stored into B. So here the two data, 8-bit of data that is stored into accumulator as well as B. Now using MUL instructions, we will try to multiply two 8-bit data. So after multiplication, the result that will be stored into A as well as B, and the data of A that can be stored into a next, RAM locations 52H, and data of B that will be stored into the 53H. Say the content of A that is 25, and content of B that is 65. So after multiplication, the data will be E99H. So the data 99H, that is the lower byte of data that will be stored into A, means into 52H, and the 0EH, that is the content of B, means the upper byte of data that will be stored into B, means that will be stored into the 53H. So that is a two 8-bit multiplications that can be done by using 8051 microcontroller. Next, 8-bit division. Here the starting address is 0000H, and the content of 70 that will be stored into A, and the content of 71 that will be stored into B. So we have to divide A by B. So after division, the result that will be stored into A means 52H, and the remainder that will be stored into B, and that will be stored into the 53H. So now here actually we can take an example. The content of A is say 95 and the content of B is 10. So after dividing it, we will get the data 9 and the remainder as 5. So 9 that will be stored into A, so means that will be stored into 52H, and remainder 5 that will be stored into B, means that will be stored into the RAM location 53H. So that is the division in operations that can be done, 8-bit division operation that can be done in case of 8051 microcontroller. Next, we will try to write a program to add two binary coded decimal data. Two BCD number additions will be there, and this is basically two numbers basically stored in 50 and 51H locations of the RAM. And after the addition, the result that will be stored into 52 and 53H of the RAM locations. So now the here the starting address is 000H. So now the content of 50H that will be stored into the accumulator, and addition A, 51H means the content of 50 and 51 that will be added. So now after addition, the result that will be stored into A. Now we have to adjust the decimal, that's why we actually use DAA. So we already know the meaning of DAA. So here the DAA is basically used to adjust the decimal. We actually take an example here. So here the two data that is stored into A and R1. So after addition, the result is 41H. So here the lower nibble, the auxiliary carry is generated. That's why 6 is added to with this instruction. So means the data will be 47. So in the next example that we are seeing that two data that is stored into A and R1, after addition the result will be AB. So A and B both are the two nibbles are greater than 9. That's why we have to add 6 in the both nibbles, means 66 is added with the AB and the result will be 11. So that is the way the decimal that can be adjusted. So here that's why we have to use DAA. After addition, the data is not decimal, so that's why we have to convert it into BCD form. So that's why we have to use the DAA instruction here. So after the decimal adjusts, the data that will be stored into the 42H. So now here the after addition carry may be generated, so we have to check the data. So that's why 00 is stored into the accumulator, and we will use the instruction add C so that the content of A and 00 and if the carry is generated or not, we don't know. So the data stored into the carry, that will be added here, and the result that will be stored into the accumulator. If carry is generated, then the result that will be 1. If it is not, then that will be 0. And the data, the result that will be stored into the next memory location, that is the 43H. So this is the PCT number addition to be now next. Write a program to clear 6 RAM locations starting at RAM address 2000. So 6 locations that is started from 2000, we have to clear the RAM locations. So here first we have to initiate the 2000 address into the DPTR. So we will write 2000 into the DPTR. Now we will clear the A. Accumulator is clearing the to clear the A, we have to write CLR A so that we can clear the accumulator. Now next, MOV R1, 06H. So we have to basically clear 6 data, and that's why we are writing 6 here to create a counter. So now next, MOVX at DPTR, A. The content of A is 0 here, so we will send the data into the at DPTR, means at 2000. So means the 0 that will be stored into 2000. So now that is clear the data of 2000. Now next we will increment the DPTR, means that will be 2001, and we will check DJNZ R1, means whether R1 is 0 or not. That is stored 06, then that will be decremented by 1, and the loop transferred into the here section, so that the program sequence that can be transferred here, and it will continue the loop until the R2 get as 0, R1 get as 0. So when the R1 made as 0, at that time the program actually ended. So basically by using these instructions, we can clear the RAM locations, and this is the program by which 6 RAM locations are cleared. Now next program, write a program to compute 1 plus 2 plus 3 plus n. Here the n is basically 10. So now and save the sum at 50H. So here that is origin starting address, and here basically we are a constant is basically is generated without storing the data, that is the 10, by using EQU. So n EQU 10 is here the constant data is assigned without storing it. So now MOV R5, has 00 each. Here the 00 that will be stored into R5, and then clear A, we will clear the accumulator. Now here the INR R5 means we will increase R5 by 1, then we will add A with the R5, the content of R5. So here the first initially it is the content of accumulator is 0, and the R5 incremented by 1, so that is 1. So 0 is added with the 1, the result that will be 1, that is stored into the accumulator. And CJNE basically check the R5. When the R5 is 10, then the operation basically completed. So now the R5 that will check whether it is 10 or not, and CJNE is basically R5 that is compared with the N, that is as 10. So it will compare R5 with the 10, and if it is not same, then it will jump here. Again it will increment the R5 by 1, then again it will add the result that is stored into the accumulator and with the content of R5, and again it will check the CJNE R5, has N, means the R5 and N are the same or not. When the operation is completed, means R5 is set as 10, so at that time that will be same, and the loop is already completed. Now the content of A, means the result, that will be stored into the 50H. So that is the end of the program by which 1 plus 2 plus 3 up to N that can be added with this program. Next, 5 8-bit numbers are stored in internal data memory from location 40H. Write a program to increment the data. So assume that the 5 8-bit numbers are stored in internal data memory from location 40H. So hence R0 slash R1 must be used as a pointer. So here the origin address is this 0, and MOV R0 comma hash 40H. So 40H is stored into R0, and basically we initiate the address here, that is storing 40 into the R0. And next MOV R5 comma 05H. So here 5 is stored into the R5 to create the counter, and hence increment at R0 means the content of R0 that will be incremented by 1. So the here R0 is 40, then it will be incremented by 1, that will be the 41, and the content of R0 that will be also incremented, that is R0 is here the 40. The content of R0 means that will be incremented by 1, means the content of R0 that will be incremented by 1, and here the 40H that will be incremented by 1 also. Now DJNZ check whether the R5 is 0 or not. Here the R5 is a counter that is set as 5. So now it will be decremented by 1, and if it is non-zero, then that's why it will be decremented by 1, and then the loop that will continue up to until the R5 gets as 0. So when it is 0, the program that is ended. So that's by which by using these instructions we can basically store the internal data memory from locations 40H. So that is a way we can increment the data from RAM locations 40H, and up to 5 data we can increment the data. By using this kind of program, we can increment a lot of data starting from our memory locations of the RAM. So that's all. And in this lecture I already discussed different bit manipulation port programming as well as different arithmetic instructions. So program using arithmetic instructions. So thank you.